we've now finished analyzing the 3 different modes of the ideal gas, and we can put all these together to look at the final picture. So putting everything together, we now have a more or less complete understanding of the diatomic ideal gas. And it looks like follows. The total partition function Z is a function of the temperature of the gas and the volume that the gas occupies, and this is 1 over m factorial. This comes from the fact that the particles are indistinguishable, times the product of the translational part, which is the first thing we calculated, times the rotational part, only depends on the temperature, and then today the one we've calculated, the vibrational part. So the total partition function is a product of the partition functions for each part divided by m factorial for the fact that the particles are indistinguishable. Okay? Now this implies that the total energy is a sum of the energies. So this is a product, but U is defined as a log of Z, so U becomes a sum. So it's the sum of the translational parts of the energy, which in fact is only a function of temperature, plus the rotational part, plus the vibrational part, and the same is true of the heat capacity, CV. Temperature, this also only depends on temperature. Heat capacity is also a sum of the translational parts and then the rotational, the rotational parts and the vibrational parts. Okay. So we can see what the total heat capacity looks like by adding up all of the parts for each mode of energy. So first of all, the translational part. We calculated a few weeks ago, we showed that the translational part of the heat capacity constant volume is pretty much constant, 3/2 kb. And this is true down to very low temperatures. If you go really, really cold, like to millikelvin ranges, then this is no longer true. But what happens depends upon whether the particles are bosons or fermions, so I will ignore that for now. Next semester, in next semester's class, we're going to look at what happens when you go to really, really cold temperatures. But for now, you can just assume that this is more or less a constant. So that's the translational part. The rotational part we calculated last time, and this gives you a graph that looks like this. This is not constant, but we showed that at high temperatures it's approximately equal to kb. Okay, and then the shape of the graph exactly depends upon the kind of molecule you've got, but typically it looks something like this. It goes to kb at high temperatures. Okay. And an important question is, what's the temperature scale here over which the heat capacity starts to increase? So this means, when do the rotational modes start to be excited? At what temperature? And we showed that the characteristic temperature T is of the order, in this case, h bar squared over the moment of inertia of the molecule times the Boltzmann constant, which for most molecules is of the order of 10 Kelvin. So at the temperatures of about 10 Kelvin or above, you start to excite the rotational energies in the molecules. Finally, the vibrational part is what we did today. And again, we can summarize this by a picture, exactly the same one I drew before the break. Okay, it has a very similar looking shape to the rotational part. At low temperatures, it is exponentially suppressed, and at high temperatures, it approaches the Boltzmann constant. But a very significant difference between these two cases is the characteristic width here. In the case of rotation, it's about 10 Kelvin. But for the case of vibration here, sorry, I'm trying to fit everything on the same board. So for the case of vibration, T is of the order of h bar omega divided by kb. And for typical molecules, this turns out to be not 10 Kelvin, but 1000 Kelvin. In other words, the vibrational excitations only occur at very high temperatures. So if you're at low temperatures, or even at room temperatures like this, there is very little vibrational energy in the gas. It's almost all in the form of rotation and translational kinetic energies. So we've got these three results. The translational part is more or less constant. The rotational part looks like this over scales of 10 Kelvin. The vibrational part looks like this over scales of 1000 Kelvin. So to find the total heat capacity, we just add them all up. So if we find the total heat capacity, it looks something like this. Draw it big. At very low temperatures, this is 0, and this is 0, so you only have the translational part. So at very low temperatures, this is about 3 over 2 kb. As I go to higher temperatures, the rotational part starts to be excited, and the rotational part adds another kb. So the rotational part gets me from 3/2 up to 5/2 kb. And its shape is the same as the shape there. This. Okay, and the temperature over which this happened is about 10 Kelvin. Then I have to go to much higher temperatures. And at much higher temperatures, I start to excite the vibrational part. The vibrational part adds 1 more kb. So the vibrational part gets me from 5/2 kb up to 7/2 kb. So at very high temperatures, the heat capacity will increase again to this value. And the characteristic temperature at which this happened is thousands of Kelvin. Okay, so we get a graph which looks like this, adding them all together, and hopefully, you may not remember, but at the start of, well, not the start, about the 6th week of the class, I showed you this graph, which is for the graph, the experimental result, the heat capacity of a diatomic molecule. Okay? And you see that the shape of the graph is exactly the same. Right? This graph and this graph look the same. But now, before I just told you this result is true, but I didn't explain why, but now you understand why. Okay? Originally it's 3/2. That's because only the translational part is excited. Well, you reach certain temperatures, as I said, this is about 10 Kelvin, the rotational modes start to be excited, and you go up. And as you go to higher temperatures, the vibrational parts start to be excited, and you go up again. So this is the graph I just showed you and said this is the result, but now we understand this result theoretically. It's a sum of 3 parts, the translational part, the rotational part, and the vibrational part. Okay. It also explains something about the equipartition theorem. If you remember, okay, let me look at this one now. The equipartition theorem was a theorem from classical statistical physics, and it said that each time you get a term in the energy which looks like something squared, you should get half kBt. Each variable which is like q squared in the energy gives you a half Boltzmann constant. This was the rule. And we said that what does this mean? For a diatomic gas, there are 3 terms which are translational, moving in the x, y, and z directions. So that's 3 halves kb. And that's the same as the result we found here. It starts off with 3 halves kb. Then the rotational part, there are 2 terms, because it can rotate in this plane or that plane. There's 2 terms in the rotational part. Now that gives you an extra k. That's the same as we found, but this term, according to the full analysis, only occurs at high enough temperatures. So the rotational part is only true if you go to temperatures much bigger than 10 Kelvin. The vibrational part, which again has 2 terms, is only true if you go to temperatures much higher than 1000 Kelvin. So at room temperatures, these two, the translational and the rotational parts, contribute, but the vibrational part does not contribute. And this is why the equipartition theorem, as stated here, is incorrect. It's only true at very high temperatures. Right, so this is the final result of this course. Okay? We've been able to explain a quite complicated graph using statistical physics, okay, and using a simple model of non-interacting molecules which rotate like a little bar and which vibrate like a little spring. So it's quite a simple model, but it can explain quite complex behavior.